Hello, good evening to everyone. As I was writing these equations for you, so I thought let me put this one on record. So I am going for a video. I don't know whether it will be helpful to you or not, but let me try by this way once. Your feedback, suggestions are always welcomed. So the only intention here I have is to explain this particular concept to you, that is two single degree of freedom system pendulums, simple pendulums, are attached here with a spring in between, this one. So this is one pendulum, this is another one, and these two pendulums are attached with a spring, and that spring is at a distance a from the point where these pendulums are hinged. And another assumption here is that this rod and this rod, both pendulum rods, are massless. Okay, so what we have to do here is we have to write the vibration equations after drawing the free body diagram for these two pendulums. So what I have done here is, as you can see here in this diagram, I have given theta 1 angular displacement to pendulum 1 and theta 2 angular displacement to pendulum 2. So obviously theta 1 is not equal to theta 2 in my assumption here, because I want some compression or expansion in this spring also. So if theta 1 is equal to theta 2, then this spring will not compress or expand. So what I am assuming here is that theta 1 is not equal to theta 2, and then I am drawing the free body diagrams. So I am getting one call, so once I have to stop this one in between. Okay, so welcome back. So what I was telling you is that I have given some angular displacement to this mass m1 and m2, that is theta 1 and theta 2 respectively, and where theta 1 is not equal to theta 2. Now what I will do, I will draw the free body diagram of this pendulum and this pendulum separately. Here also I have drawn the free body diagram, but I think this is not visible clearly. So what I am doing here is I have drawn the free body diagram separately. So look at here, the gravitational force or due to self weight of this mass m1 is m1g acting vertically downward here, and as spring is having relative displacement, because see this end of the spring is moving from here to here. So this is not the actual compression in the spring, because when this end of the spring is coming from here to here, that time this end of the spring is also moving in forward direction. So we have to take the relative displacement, that is this displacement minus this displacement. Now what is this displacement? This one. How much is this displacement? This one. Can you tell me how much is this displacement? This one. So this one is, this distance is a, and this angle is theta 1. So can I say this displacement is a theta 1. Similarly this is a theta 2. So what is our relative displacement? That is a theta 1 minus theta 2. So this is the actual relative compression in the spring. So if this is the relative compression, then what will be the force? Force will be displacement into stiffness. So that is K into A, which is here, into theta 1 minus theta 2. So that's what I have mentioned the same here. That is K theta 1 minus theta 2 into A. So this is one force and this is another force. Similarly in this free body diagram also these two forces. But remember here theta 2 minus 1, as we are drawing the free body diagram for mass 2. So 2 I will write first and then I will write 1. So here I will write the D'Alembert's equation. That is for this free body diagram. First I am writing for this one. So what I have to do, I have to take the moment of all the forces about the point about which this pendulum is rotating. So here two forces I am having. This is those two forces are, first one is mass m1g, force m1g, and second one is k theta 1 minus theta 2 into a. So you can see here I have written the torque due to first force, that is gravitational force. So force, once forget about the negative sign, don't see this one. So see here that force, that is m1g, into distance. So which distance we have to take? We have to take this distance. For this force m1g, we have to take this distance, this one. This one we have to take the torque, right? So what is this distance? This length is L and this angle is theta 1. So this component is L cos theta 1 or L1 cos theta 1, and this perpendicular component will be L1 sin theta 1. So sin theta 1 I have written here theta 1. So L1 into theta 1. So why I have put here negative sign is because my pendulum is moving in this direction, that is anti-clockwise like this, and the force which is m1g is producing a clockwise torque, so opposite to the direction of motion. That's why I have written here negative sign. Similarly, torque due to this force, so force into simply distance, that is a. So I have done here a square, and one more torque will come, that is inertia torque, that is I theta 1 double dot. So this sum of all these torques must be equal to 0. So this is my equation 1. Similarly, for this free body diagram, torque due to this force, that is m2g into this distance, this one, as I have taken here this distance. So similarly here also distance will be this one. So this distance is this one, and this distance is L theta 2. Actually this will be L sin theta 2. So sin theta I am writing as theta. So see here I have done the same thing. Force, that is m2g into distance, that is L2 into theta 2, and negative sign is here because this torque is in opposite direction of the rotation of the pendulum. And simply this spring torque is force into distance a, and inertial torque. So these are two equations I am having. I have written these two equations in a form of a matrix, that is I1 0 0 I2. So this is a diagonal matrix, and second property symmetric, and a matrix of 2 cross 2. So these are the properties this matrix is having. Why this matrix is diagonal, that you can observe from here. That's very simple. You have taken the coordinates where or the point about which the your pendulum is rotating. So this is the simple reason because of which we have taken because of which this matrix is coming diagonal, and these terms are, I have mentioned from here only, equal to 0. So if you put theta 1 equal to phi 1 sin omega t and theta 2 equal to phi 2 sin omega t, then you will be getting your solution. That will become that solution will be coming in form of omega 1 square, omega 2 square. So these are your two natural frequencies, but we don't know which one is the fundamental or first frequency. So to check that one, what you have to do, you have to calculate the mode shape, that is phi 1 divided by phi 2. So in one case this will be positive, and in another case this will come negative, right? So this is very simple problem that I have explained to you here. I hope this will be helpful to you. Thank you so much.